Assalamu alaikum, dear students. This is this is 11th chemistry, and our today's topic is dual nature of radiations, or de Broglie's equation. Now, as far as this de Broglie's equation is concerned, actually, the dual nature of electromagnetic radiations, it was already established that these electromagnetic radiations, they possess a dual nature. That means they have got a wave character as well as the particle character. Now, as far as the wave nature of these electromagnetic radiations is concerned, we have got various phenomena like we have got diffraction, we have got this polarization, we have got this refraction, reflection, and all these effects or these phenomena suggest that these electromagnetic radiations, they have got a wave nature. Now, as far as the particle nature of these electromagnetic radiations is concerned, and it was rather observed by Einstein that when these electromagnetic radiations are made to strike on a metal, photoelectrons get ejected out from this metal surface. So this is known as photoelectric effect, as it was given by Einstein. Now, as far as this photoelectric effect is concerned, it suggests the particle nature of these electromagnetic uh, radiations. Now, de Broglie, inspired by de Broglie in 1924, inspired by this concept of the of electromagnetic radiations, that is a dual nature of these electromagnetic radiations, suggested that matter material particles in motion, whether microscopic or macroscopic particles, they also possess a dual nature. That means they also behave sometimes as wave and sometimes as particle. Now, according to de Broglie, the waves associated with these material particles in motion, they are called as matter waves. Now, he derived a relationship that relationship, or he gave an equation which is known as de Broglie's equation, and this equation he derived from the two concepts, taking the concept of this by from the concept of this Planck's quantum theory, and Einstein's this mass energy equation. Now, according to Planck's quantum theory, electromagnetic radiations are absorbed or emitted. Not electromagnetic radiations are not emitted or absorbed continuously, but discontinuously in the form of small energy packets, what he called as uh, as contours, what he called as contours. Now in case of these in case of this light, these energy factors, they are called as photons. Now, the energy of these contours is given by the equation E is called h nu, where nu, it is the frequency of these contours, and h is the Planck's constant, E is the energy. Now, we know the frequency of this quantum is given by c over lambda, where c is the velocity of these velocity of these electromagnetic radiations, or velocity of these contours, and lambda is the wavelength. Now, as far as this so E is given by, that is the energy of this contour, as per this Planck's quantum theory of electromagnetic radiation, is given by, energy is given by hc over lambda. Now, as far as Einstein's mass energy equation is concerned, according to Einstein, mass can be converted into into energy when light falls on it. So he gave a relation that is called E is given by E is equal to mc square, where m is the mass and c is the velocity of these these radiations or these energy factors or quantas. Now, now equating these two equations, Planck's quantum theory and this Einstein's mass energy this equation, we get an equation that is given by lambda is equal to hc over mc square or h over mc. Here mc, it represents the momentum of this of these photons, or momentum of these quantas. Now lambda, as it is given by h over mc. Here h represents it is the Planck's constant, and mc, it is the momentum of the quantum, or momentum of the photon. So this equation, that is lambda is equal to hc, it is known as de Broglie's equation. Now in this equation, this is now if this now here c is the velocity of the light. Now if we represent the velocity of the moving particle, then the above equation we can write it as lambda is equal to h over mv. Now mv, as it is the mass, it is the product of mass and velocity, that is the momentum, or we can say lambda is equal to h over p. Now this equation, this is known as de Broglie's equation. It relates, or in this equation we see that the wave nature and the particle nature, they are inversely proportional to each other. So that means if the wave nature increases, particle nature decreases, or if the this particle nature increases, then the wave nature decreases. Now as far as this de Broglie's wave equation is concerned, this limitation is that this equation, it holds good only for these microscopic particles, like we have got electrons, protons, neutrons, atoms and ions, because in these particles we see that the particle nature is extremely small, so the wave character is very significant. Now being significant wave character of these particles, because of the significant wave character of these particles, we can this the wavelength of these particles can be easily calculated. Now as far as the microscopic particles are concerned, or the microscopic particles, now the particle size is very large. So particle size being very large, the wave character is very negligible, so it is not possible to calculate the wavelength of these microscopic particles, like a moving cricket ball, where we see the particle nature is where we see the size is very large. So the particle nature is very large. Now the wave character is extremely negligible. Now this de Broglie's equation, as far as it is this merits are concerned, this equation was very helpful in establishing the dual nature of the electrons. Now as far as the electrons are concerned, we see that these electrons, they have got a particle nature, because they have got a mass, they have got this they have got mass, they have got this their charge, and they have got their energy and momentum. This suggests the particle, these characters, they suggest the particle nature of these electrons. And similarly, we see in case of scintillation, when these electrons are made to strike against zinc sulfide screen, we see bright spots are observed on this zinc sulfide screen. This is known as scintillation, and it has been found that only one scintillation is noted. Only one scintillation is one scintillation spot is observed for one electron. So this suggests that electrons have got a localized behavior. That means they have got a particle nature. Now another this theory which suggests that particle particle nature of these electrons. We have got this black body radiation, black body radiation. We have got Einstein's photoelectric effect. These both these effects, or both this Einstein's theory and this black body radiation theory, it suggests that electrons, they possess a particle behavior. Now, as far as this wave nature of electron is concerned, it was this was explained, or it was confirmed by Davison and Germer in 1927. They suggested that these electrons, they possess a wave nature. Now, what they did, what these Davison and Germer did, they got an electron beam from a red hot tungsten filament, and this electron beam was accelerated under the influence of this electric field, and it was made to strike uh, against this nickel crystal, and different these dark and these bright rings were observed on a photographic plate. Now these were called as diffraction rings. Now these because of these diffraction rings suggest that these electrons, they have got a wave character. Now their diffraction the diffraction pattern as got by this Davison and Germer, it was very much similar to the diffraction pattern of the X-rays. Similarly, Thomson, he also performed the same experiment, but what he did, instead of nickel crystal, he used this thin foil of gold, and found that a similar diffraction this pattern was observed. This clearly shows that these electrons have got a wave nature. So this de Broglie's equation, it was of great rather significance in explaining the dual nature of these material particles in motion. Now, as these have been separately, they have been confirmed by this Davison and de Broglie, and we show the wave nature, and this what we call as this photoelectric effect. Similarly, with these various these evidences, they support that these material particles, when in motion, possess this dual nature. So this is enough for today. Thank you very much.